And so today, or tonight for some of us, it's our pleasure to welcome Denis Hirschfeldt, who is going to talk about minimal pairs in the generic degrees. So please.
Great. Thank you, Lubik. And definitely want to thank all the organizers, well, for inviting me, but also just for generally organizing this really great seminar series. And thank you all for being here from all the different corners of the world and time zones. So yeah, definitely, if you have questions or whatever, figure out some way of getting my attention. I can't see the chat, but anything else I'll probably notice. So I decided to give this talk, well, I do have a relatively recent result to talk about here, but also, and mainly because there's a lot of open questions that I find interesting, and I'm hoping to maybe get some people interested in them. So this talk is about the notion of generic computability and generic reducibility, which is a notion of almost everywhere computability for sets of natural numbers. So we begin with that. Of course, in the natural numbers, we don't have a notion of measure, but there's a good notion of density that allows us to talk about almost everywhere behavior. So in particular, a set of natural numbers has density 1 if the proportion of numbers less than n in the set goes to 1 as n goes to infinity. So now we can define a generic description of a set A is a partial function, a partial 0, 1 valued function, f, whose domain has density 1 and that is equal to our set or the characteristic function of our set wherever it's defined. So the idea is that it's a description of a set that always gives the correct value, except once in a while it doesn't give any value. Right? It doesn't actually give you an answer. So here's a picture of it. Here's our set A, and here's like a generic description. If you check, if I did things right, all the things are the same color, except there's a few holes. And the idea is that as you go along, the holes get rarer and rarer. Now, there's no computability theory here yet, but of course, we can then talk about computable generic descriptions and say that a set is generically computable if it has a partial computable generic description. So this notion goes back to work of Kapovich, Myasnikov, Shoup, and Spielrein, and they were looking at problems in group theory. In particular, there's a lot of problems there that are difficult, either in the sense of having high complexity or even of being undecidable. And yet, the cases that generate this high complexity are very sparse. So on a set of density 1, you might have a very easy algorithm. And they want to capture this idea. There is a notion of average case complexity, but it's famously unwieldy. And so they introduce a notion of generic case complexity, and then also generic computability. And then later, Jacques and Shoup started looking at this from a computability theoretic point of view, and it's generated quite a bit of work, some of which, but certainly not all of it, I'll talk about today. Now, this is not the only notion of almost everywhere computability. There are other ones that have been studied. So one that also was looked at by Jacques and Shoup is the notion of coarse computability, coarse descriptions. So if a generic description is one that always has to give the right answer, except sometimes it doesn't give an answer, a coarse description is one that always has to give an answer, but sometimes can lie. So a coarse description of a set A is a set D, or if you want a 0, 1 valued, total 0, 1 valued function, D, that is equal to A on a set of density 1. So again, we have our set A, and now we have our coarse description. If you look carefully, you'll see there's a few sparse places where the colors are different. So that's a coarse description. Now, of course, having done that, we could combine these two kinds of mistakes, right? The omissions and the actual outright errors, and talk about dense description. So a dense description of a set A is a partial function that converges and is equal to A on a set of density 1. But outside that set of density 1, it might diverge or it might give false values. So the picture is, again, A. And here's a coarse description. There's a couple of holes, and if you look very carefully, you'll see there's a couple of places where the colors are wrong as well. And yet another notion that's been looked at that's a little bit different, but as we'll see, very much related, is the notion of an effective dense description. So an effective dense description of A is now a total function, but a total function that has 3 possible values, 0, 1, and this box symbol, which you can read as I refuse to answer. And so the idea there is that on a set of density 1, f has to have value 0 or 1, and whenever it does, it has to actually have the correct value. But there's a set of density 0 in which I might say, I refuse to answer. So like this, and then there's a few boxes. Now this is different from a generic description. And the easiest way to think of it is to think about it the computable versions, right? A computable generic description is a partial computable function that might diverge in a few places. A computable effective dense description is a computable total function that in a few places just converges but says, I refuse to answer. So an example of this kind of phenomenon is, for example, if you have an algorithm that you know on a set of density 1 runs in some bounded time, you have some polynomial time, say, bound for it, and then it might run for a long time or maybe even never converge on other values. What you can do is you can run it on an input for that amount of time up to that bound. And if you haven't seen it converge by then, you just say, I refuse to answer. So that's a way you can generate a computable effective dense description. So of course, like with generic descriptions, you can talk about computable coarse descriptions, computable dense descriptions, and so forth, and that therefore talk about a set being coarsely computable, densely computable, effectively densely computable. And you might think that there's other versions of it, and you could say, well, what if I have both refusals and divergence and so forth? But if you actually play around with it a little bit, you'll see that up to computable equivalence, those are the only 4 actually. Well, other than the one that you don't allow any mistakes at all, then that's just computable. Now, another thing you can do with these things, of course, is you can relativize them. You can talk about being coarsely computable relative to an oracle or generally computable relative to an oracle. But you could also transform them into notions of reducibility, like this. So for example, for coarse, we're going to say that A is coarsely reducible to B if every coarse description of B computes a coarse description of A. So I think it's a pretty natural notion. It's just saying, if you can kind of give me B with a few mistakes, then from that I can give you A with a few mistakes. And you can do that for all these other notions. The one thing which actually will turn out to be quite important for us to notice, though, is that for something like generic reducibility, a generic description of a set is a partial function, not a total function. And we don't want to use the negative information about where the function is not defined. So the correct notion to use here is not term reducibility, but enumeration reducibility. So we want to say that A is generically reducible to B if for every generic description f of B, there's a generic description of A that is enumeration reducible to F. Or if you want to be more precise, the graph of the generic description of A is enumeration reducible to the graph of F. But I identify a function with its graph. So that leads to notions. I don't have the other ones written down here, but same thing for the other notions. Now, to be precise, there's actually 2 versions of each of these. The ones that I've actually written down here are non-uniform versions, but you can also imagine, or you can define a uniform version, where, for example, for coarse reducibility, you would say there's a single Turing functional that takes any coarse description of B and returns a coarse description of A. So there are non-uniform and uniform versions, and they are provably different. But until I get to the end of the talk, fortunately, everything I'm going to say applies to both cases, so I'm going to drop the distinction. Now, of course, for the open questions that I'll mention, it is possible that the answers could go different ways for 2 different notions. So that's worth keeping in mind. Another important point that's going to be important in understanding some of the results here is that saying that A is generically reducible to B is stronger than saying that A is generically computable relative to B. So here's the picture. So when I say that A is generically computable relative to B, what I'm saying is if you give me B, so B is on top here, right? So if you give me B from the full power of B, I can compute a generic description of A. Okay, but when I say that A is generically reducible to B, I'm saying that if you give me any generic description of B, I can use that to get a generic description of A. Now that's of course harder, first of all, because a generic description of B might have less information than B itself because it has a few holes, and also because you have to do it from every generic description of B, right? So there's lots more oracles to consider. So this is of course a stronger notion in general. So that's worth keeping in mind. And of course the same thing is true for the other notions. Okay, so before getting to the main topic of what I want to talk about, I want to mention one thing, to mention a couple of frankly embarrassing questions, because they're very fundamental questions that we still don't know the answer to, and I would love to. So the first one comes from this. So in the notions of computability here, we have this very nice diagram that the notion of effectively densely computable implies both generically and coarsely, and that implies density. And proving that these arrows hold is just a little exercise. If you kind of just go back to definitions, it's not hard to do. But it's also true that none of these arrows reverse, and you can get that using examples that go back to Jacques and Shoup, and you can jazz them up, and in fact, you can show that the arrows don't reverse even for C sets, and so on. But what we don't know is whether these implications also hold for the corresponding reducibilities. The non-implications, of course, do, because these are the bottom degrees in all of these cases. By the way, I should have said that. Obviously, these notions of reductions lead to degree structures in the usual way by taking equivalence classes. So these are all the bottom degrees, and they differ, so these differ. But do the implications hold? And the problem there is if you look at, let's say coarsely and densely, right? To compute a coarse description is easier than computing a dense description. But if you're saying that something is densely reducible to something else, you need to compute dense descriptions of the bottom set from every dense description of the top set, and there's more of those than there are coarse descriptions. So you're performing an easier task, but more oracles have to perform it. So there's a tension there. And so maybe my guess is that the arrows don't hold, but I don't know. I don't have examples. They might. So that's one question. And let me mention a sort of even more embarrassing question, because it's even more basic in some sense. I gave the definition of these notions for sets, but you can give the same definitions or similar definitions for functions as well. Functions for natural numbers and natural numbers. You can talk about coarse descriptions, generic descriptions, and so forth. Now, in most cases of reducibilities that I know, certainly something like Turing reducibility, we don't really make too much of a distinction because, you know, the Turing degrees of functions is the same as Turing degrees of sets, right? Every function is Turing equivalent to a set. But here we don't know. For each of these reducibilities, is every function actually equivalent to a set? And I don't know for any of them. So that's kind of embarrassing that's open, but that's there. Okay, so let me move on to the main topic here. So as I said, from each one of these notions, you can derive degree structures, and you can ask the kind of usual basic structural questions that one asks about them. And one example that goes back to the paper of Jacques and Shoup. And I should say, by the way, before I do that, that there's an interesting little prehistory that I forgot to say, that some of these notions had actually been looked at before all of this work. So the notion of effective, so just to go back here just 1 second, the notion of effective dense description at the bottom here actually goes back to the 70s. There was a question that was asked by Albert Meyer in the recursive function theory newsletter, which is an old sort of dead tree blog in the 70s. And it was then answered by a student at the time, Nancy Lynch. And after that, as far as I know, nothing happened with these things until Bas Turbine's dissertation, where he looked at some related notions. The notion he was looking at, though, was coarse reducibility, as it turns out, or coarse computability. And he pointed that out to me and pointed me to the Meyer and Lynch papers. But obviously, it was with the work of Jacques and Shoup that things really got going. But that stuff did exist, and Bas's that section of his in his theory in his thesis never got published. So anyway, so let me go back to this. Okay, so, but in the paper of Jacques and Shoup, one of the questions they asked there is whether there are minimal pairs in the generic degrees. So minimal pairs are a common thing that one asks about and often answers very quickly about degree structures, right? So minimal pair, so if you have any degree structure that has a bottom degree, minimal pair can be defined as just two degrees that are not the bottom one, where the only degree below both of them is the bottom. And of course, all of these structures have a bottom degree, which is the notion of the generic computable, coarsely computable, etc. And for a lot of structures, this is even a fairly easy question, something that gets solved early on, and then one could ask about different kinds of minimal pairs and so forth. But for the generic degrees, this was open for a long time. It was asked by Jacques and Shoup, and then when certain partial results were given, it was asked again by Downey, Jacques and Shoup in a later paper, and then by Gusa, whose work I'll get to in a sec. But that was open. Now for some of the other notions, so in work with Jacques, Kuiper, and Shoup, we did show that there are minimal pairs in the coarse degrees. And in fact, we did a little more than that. We actually showed that there are minimal pairs for relative coarse computability. Now, remember I said a while back that relative coarse computability is a weaker notion than coarse reducibility. Therefore, the notion of minimal pair becomes a stronger one. it's harder to be a minimal pair for relative coarse computability. So let me just remind you what minimal pair for relative coarse computability means. It means that there are sets X and Y that are not coarsely computable, such that if a set is coarsely computable relative both to X and to Y, then it is coarsely computable. Right? So that's stronger than, that means, of course, that they're minimal pair in the coarse degrees, but that's even stronger, right? Because you only need to be coarsely computable from X and Y, not from every coarse description of X and Y. And so we proved that for coarse degrees, and then later in work with Astor and Jacques, we showed that the same holds of the dense degrees and of relative dense computability. You'll notice now that the notion of effectively dense, the one with the refusals to answer, is not here. I'll get to that towards the end of the talk. But for generic, this was open, and in fact, there was indication already, even before these results, that the kind of methods that we used here were just not going to work. And that is because of this result of Egoussis, which is part of the reason that that this question of minimal pairs was so interesting, because he showed pretty early on that there is no minimal pair for relative generic computability. Now, that's the stronger notion, right? So that does not mean that there might not be minimal pairs for generic reducibility, but for the relative generic computability, there aren't any. So in other words, what he showed is if X and Y are even just not computable, then there's a set that is not generically computable, but is generically computable relative both to X and to Y. So any two sets, non-computable sets, have some common power in terms of generically describing something that's not already generically computable. So that's a very nice result and a difficult one. And it shows that the way that we build minimal pairs for coarse computability, for dense computability, is not going to work here, because those methods, which I'll talk about in a second, do generate minimal pairs in the stronger sense, and that's impossible for generic. So that was an indication that maybe there aren't any minimal pairs in generic degrees. However, a few months ago, I was able to finally show that there is a minimal pair in the generic degrees. So I want to talk about this proof before going back to the results and saying some things. So the thing is, there's a sense in which I like this proof because I came up with it, but also no, there's a sense in which I like this proof, which I'll mention when I describe the proof, which is that it's not too hard, but my mistake, in a certain sense, I'm working on this problem for a while. One mistake I was making is I was trying to get methods that yield minimal pairs for other structures, like the Turing degrees or the coarse degrees and so forth, and trying to adapt them in some ways to generic degrees. Turned out that the right thing to do is to get a proof that doesn't work and adapt that. So I'll explain what I mean when I talk about the proof. So I like that. Now, the unsatisfying aspect is that there's some pretty special things about the minimal pair constructed here, which end up leaving more questions, I think, than it answers, which in some sense is good now. So I'll turn to these questions later. But let me talk about the proof first. So to build this minimal pair, I'm actually going to build delta 2 witnesses. So these sets X and Y witnessing this minimal pair are going to be delta 2. And in fact, they're actually also going to both have density 1. Now, of course, I could have taken the complements and have density 0. It doesn't matter, but let's say they have density 1. And I'm going to build generic descriptions f of x and g of y. Now, when building something to be a minimal pair, I could, of course, build to provide witnesses to these, for these minimal pairness requirements that I'll talk about in a second. I could have built many different generic descriptions of x and many different generic descriptions of y. As it turns out, in this proof, I only need to build one of each. Furthermore, these descriptions f and g both of them will have value 1 everywhere that they're defined. So they're basically, all that's going to matter is where are they defined. Now we need to, one thing we need to do is we need to make sure that x and y are not themselves generically computable, so we need to do some diagonalization. Now, the places where f and g are defined, the value has to be 1, so that's not very good for diagonalization. So of course, it's the places where they're not defined, x minus the domain of f and y minus the domain of g, that I'm going to use to diagonalize against computable generic descriptions. Now, f and g are themselves going to be delta 2. They're going to be 1 where they're defined, but where they're defined is going to change throughout the construction to allow for this diagonalization. Because in one way, diagonalizing against potential computable generic descriptions is pretty easy. Because remember, a generic description has to be correct where it's defined. So if I just pick a place where a supposed generic description of X or of Y is defined, and then just change that one bit, I've diagonalized, just like with regular trying to make something non-computable. The difference, though, is that these descriptions don't have to be defined everywhere. So unlike for computability, I can't just pick a witness and say, wait until the thing converges in that witness. I have to actually wait for something to converge and then take that witness. Now, that witness, if that happens to be in the domain of F, for example, then that means that I have to undefine the domain of F there and then do my diagonalization. So that's the tension. Now, so that's one part. The other part of making the thing X and Y minimal pair is this. For any pair of enumeration operators, phi and psi, if phi applied to F and psi applied to G threaten to be generic descriptions of the same set, then I have to make sure that that set is generically computable. So I have to build my own computable generic description. So if phi F and psi G both have domains of density 1, and they both agree where they're defined, which means they could be descriptions of the same set, then we need to build a partial computable function H whose domain also is density 1 and that agrees with at least one of the two where it's defined. And then any set that both of them describe, so does H. Notice, by the way, that saying that phi F and psi G have domains of density 1 means the intersection of their domains also is density 1, which means that it's fine, as long as we make sure that H is defined in the intersection of those domains, we're fine, right? So we don't need to define anything until both phi of F and psi of G are defined there. Okay, so with all this in mind, let me draw the picture here. Oh, and of course, I have to do this for every phi and psi, but I'm going to describe how to do it for one phi and psi, and putting them together is actually not difficult. Okay, so I'm building X and Y, but in my picture, what I'm looking at is the descriptions F and G of X and Y. They have a few holes. And then there's a set in the bottom there, which they might be both phi F and psi G might both be generically described. So we approximate F and G to be generic descriptions of X and Y, respectively, and we ensure that X and Y are not generically computable. And at the same time, we monitor these phi F and psi G, and we build our computable H to describe the same thing that phi F and psi G do, as long as they both describe the same thing. Okay, so here's what might happen. Phi F might enumerate n0. That is, phi F says the value of the set at n is 0. So that can happen, and I've drawn the use here in red. Now, we don't have to do anything yet because the G side hasn't said anything. But now, of course, psi G also enumerates the same value. At this point, n is in the intersection of the domains, the values agree, so we really have no choice but to define H of n to be 0. Now, notice that we are defining H to be a computable object, partial computable object. Therefore, we can't go back on that description. So now we have to make sure that at least one of the two sides keeps that n0 enumeration, right? We don't care which, but at least one of them has to do. So what's going to happen? Well, for diagonalization reasons, to help make X not generically computable, a diagonalization requirement might have to violate the use in the F side. It might need a number to act as a witness, and that number might be in the domain of F, so it has to remove it from the domain of F. So if you look carefully, a box goes away. There were 4 holes below the use, now there's 5. And so now the use has gone away. We're still okay because things are still okay on the other side, right? And if you have a weaker requirement than the one that destroyed the computation on the F side, we can restrain it from violating the use on the G side. That's fine, right? So it might change something, but only above the use, right? So here, a hole happened at the end there. And that's fine. That doesn't change anything. But of course, in the usual fashion, there are going to be stronger requirements. So a stronger requirement might want to violate the use on the G side. And what we would like to do is restore the F side. That's fine as far as the requirement that destroyed the F side. It now gets injured, but it got injured by a stronger requirement. That's fine. So we would like to restore. So notice that on the F side, there's like 5 holes now. The thing on the G side goes away. So we would like to restore the thing with 4 holes on the F side. Believe me, this is what it was in the previous state. Okay, so that would be great. However, we might not be able to restore it to this previous state because of other enumerations. After all, I mean, we're monitoring only one thing, but obviously there might be some other values. For example, notice this 1 here. That might be another thing that we're trying to preserve, right? So now, to explain how this kind of works, let me go back to the situation where it doesn't work. Let's suppose we were trying to do the same kind of construction to build a minimal pair in the Turing degrees. So then we would just be building X and Y. We'd be monitoring these two, in this case, would be Turing reductions, phi X and psi Y. 5x would be giving you a value. The maybe psi y gives you the same value. The computation on the x side goes away. Computation on the y side goes away. Now you want to restore the x side. But there might be two different values that you were preserving, right? One of them might have happened, the computation might have happened at stage 13, and the other one at stage 100. So you'd want to restore x to what it looked like, at least up to the relevant use at stage 13, and you also want to restore it to what it looked like at stage 100. That's a problem, right? These two things might be incompatible. So in general, there's no way to restore a set to what it looked like both at this stage and at that stage, right? So that just doesn't work in the Turing. No, not without modifications. But here, we have two things going for us. First of all, f is 1 wherever it's defined, right? It's always 1. So, and also, we're dealing with enumeration reduction. Now, the enumeration reduction does not get to use negative facts, right? So if I give you more convergences of f than there were when that enumeration happened, the enumeration still happens. So if I have something that happened at stage 13 on the f side and something at stage 100, those are fully compatible. Just take the union of those two functions, and that's actually okay with both of them, right? Because the only thing that's going to happen relative to both of them is you have more places where you're defined, and that can't change the enumeration. So we might not be able to restore f to its exact previous stage, but we can restore it to an extension of that stage. So the previous stage here had 4 holes, and now we restore to one that has 3 of those holes. And that's still okay. The enumeration still goes back because it's an enumeration reduction. So there's no incompatibility, and that's it, and it just works. So that's the proof. Okay, so that gives you a construction of minimal pair. I was happy to get it, but as I said, there's some things about this, right? So one thing is the sets X and Y built are pretty special. They're delta 2. They also have density 1, which means in particular they're coarsely computable, right? Because anything of density 1 is coarsely computable because the full natural numbers are a description of any set of density 1, so trivially coarsely computable. So that's kind of special. Now for coarse reducibility and for dense reducibility, we have a very different situation for what we know. For those, things look a lot more like the Turing degrees. So going back to this paper with Jacques, Kuiper, and Schub, we showed not just that there are minimal pairs in the coarse degrees, we showed that there are measure 1 minimal pairs in the coarse degrees, just like in the Turing degrees. In fact, every non-zero coarse degree forms minimal pairs with measure 1 many coarse degrees, just like with Turing reducibility. Indeed, we actually have a stronger result. Well, on the one hand, because it's about coarse reducibility, relative coarse computability, but also because, well, you see measure 1 kind of results, and if you have any interest in algorithmic randomness, you want to kind of ask, can you quantify that in terms of randomness? So what we actually showed is that if X is not coarsely computable and Y is weakly 3 random relative to X, then X and Y form a minimal pair, even for relative coarse computability. So obviously this is a result we're not going to be able to get for generic because of Igusa's result that there are no minimal pairs for relative generic computability, but maybe we can rescue a degree version. So with Asser and Jacques, we also showed that the same holds for dense computability, but there we needed weak 4 randomness. Now, for those who are interested, in the case of coarse computability, we're able to show that you can't improve weak 3 randomness to 2 randomness. But in the case of dense computability, we don't know how optimal weak 4 randomness is. You might be able to get away with less. So let me say something about how these results are obtained, but going back actually to Turing reduction, one way to get minimal pairs there. So there's this very well-known classic result, first proved by DeLu, Moore, Shannon, and Shapiro, and then stated in this precise form and proved independently a little bit later by Sachs, that if a set is not computable, then its upper cone, the set of all y's that can compute A, has measure 0. This is measured in the usual sense-Lebesgue measure. So from that, I think it's a really nice result. It's one of those results in computability theory that I've actually been asked about by people who didn't know the result and weren't actually mathematicians, right? In various forms, right? People ask a question like, well, you're telling me the halting problem is not computable. Well, what if I had like a random source? Could I then compute it, right? That kind of question, right? So you can answer it with this result. And you could also get minimal pairs there because take an X that's non-computable. I'm choosing X to be non-computable just so it can be half a minimal pair. Now, the set of A's that are computable from X is countable. So now I can take all of the A's that are computable with X, but not computable, right? And look at all their upper cones. Each one of those upper cones has measure 0. There's countably many of them. So the union still has measure 0. So that means that there's measure many Y's that are not in those cones, not in that union. Well, if you're not in that union, that means you can't compute any non-computable set that X computes. That is, X and Y form a minimal pair. So that's how you get measure 1 minimal pairs with X as one of the halves. That's one way to get it. And in fact, if you care about the randomness, if you look at the complexity of the set, being weakly 2 random relative to X gives you that property. 1 randomness is known not to be enough. So at the level of course, so when you move from, it's interesting, move from Turing reducibility to coarse reducibility, you move from weak 2 randomness is enough, 1 randomness is not, to weak 3 randomness is enough, and 2 randomness is not. There's an interesting jump there.
I just have to say, I really like this proof, Dennis, that you have measure 1 many minimal pairs, right? It shows you that minimal pairs are very natural things to look at, right? I mean, they occur everywhere.
Yeah, absolutely. And yeah, and also it is to some extent adaptable. So in these 2 papers that I mentioned before, we showed for coarse in the first paper and for the other ones in the other one, that not all these non-trivial upper cones are also null for relative coarse, generic, dense, and effective dense computability. So all of those have null upper cones, which is kind of what you would expect, but you need to show it. And to do this in the paper, when we did it with it was a slightly different method for coarse reducibility, but then in the paper with Asser and Jacques, we had a kind of a uniform method for doing that using this nice little lemma, which is basically a Fubini theorem, but instead of exchanging measure and measure, you exchange measure and density. Now, given this result, you can then try to do a version of this proof to construct minimal pairs. And for coarse reducibility, it works. And for dense reducibility, it works. It's not 100% obvious, but you have to play with it. For example, for coarse reducibility, the basic fact that you use is that a coarse description of a coarse description of X is still a coarse description of X. And then you can kind of play with it, and it works. But if you try to do that argument for generic reducibility or for effective dense reducibility, it doesn't work. So if you want to know why, just try to do the argument, and it's not going to work. But for those, from this result, we get this result, right? That you have measure 1 many minimal pairs in the coarse and the dense UEs. So that raises a lot of questions. For example, the minimal pairs that the minimal pair that we saw for the generic degrees are both sides are delta 2. Are there non-delta 2 minimal pairs in generic degrees? No idea. On the other hand, maybe minimal pairs in generic degrees are really special. So remember, both halves of the minimal pair that we built up there are coarsely computable. So must minimal pairs in generic degrees involve coarsely or at least densely computable sets? So maybe both halves have to be coarsely computable. Maybe at least one half has to. Maybe at least one half has to be at least densely computable. And I think there may be some stuff that can be mined from the work of Igusa there, but I'm not sure. Conversely, I mean, on the opposite direction, maybe there are lots of minimal pairs. Maybe there are measure 1 minimal pairs in the generic degrees. In fact, maybe every non-zero generic degree is half a minimal pair. Maybe every non-zero generic degree is half a minimal pair with measure 1 many other things, right? So it's possible that it's all the way like the coarse or the Turing case. So of course, these are just example questions. The general question is, what can you say about the distribution of minimal pairs in generic degrees? Are they really, in particular, are they really, really special and maybe close to computable? So in a similar kind of, in some sense, a similar kind of phenomenon that you have an algorithm randomness like K-trivials that are not computable, they're really close to computable and have lots of properties, weird properties that you wouldn't want to exist maybe, but they do. But there's very few of them. Or maybe they look a lot like the coarse degrees and the Turing degrees, and there's actually lots of them, and I just haven't figured out how to build them. On the other side, for coarse and dense degrees, I don't know whether there are delta 2 sets with coarse or dense degrees for a minimal pair. Now, of course, you can have 1/2 this delta 2, but I don't know if you can take 2 delta 2 sets that form minimal pair in the coarse or the dense degree. So what we know about the coarse and the dense case is sort of exactly what we don't know in the dense case, and vice versa. So that's why I say the result's a little bit unsatisfying, and there's a lot more to ask. Let me mention some older related questions I think are still quite interesting. So this goes back to the work of Jacques and Shoup and the work of Igusa. One thing that's worth pointing out, of course, the minimal generic degree would be half a minimal pair. That's true in, well, I was going to say every degree structure, but okay, you also need to know that you don't have upper cone that includes every other degree, right? So combined with the fact that we know that upper cones and the generic degrees are small, if you have a minimal generic degree, its upper cone is measure 0, so take something that's not in its upper cone, then it has to form a minimal pair with it. So that would be a way to get a minimal pair, but a question that goes back to the paper of Jacques and Shoup and is still open is whether there are many minimal degrees. So we don't know that, and in fact, we don't know that for any of our notions. We don't know that for coarse, dense, effectively dense, so that's completely open. Now, one thing that Igusa did show is that a density 1 set can't have minimal generic degree. So the sets that, in the construction that I gave for minimal pair, those definitely are not minimal. So that's a completely different kind of animal. In fact, Igusa noticed very early on that density 1 sets seem to be, understanding density 1 sets seems to be important to understanding the theory of the generic degree. So this is in a couple of papers of him. And then there's a paper of Cholak and Igusa as well that continues that work. In particular, he showed that, and here, this result he proved only for the uniform version of generic reducibility, but forget that for a second. A generic degree that doesn't bound a non-zero generic degree of a density 1 set has to be half a minimal pair. So if you don't have any non-trivial density 1 sets below you, then you're half a minimal pair. So he showed that. So that was a way of trying to get a minimal pair. But of course, the sets that in the construction I gave for a minimal pair, they actually have density 1, right? So again, very, very different kind of thing. And in fact, we don't know, does every generic degree bound a non-zero generic degree contain density 1 set? Igusa showed that either of the directions answering that would be interesting. So if the answer is no, then by the theorem just above, that means that you have a different way of constructing a minimal pair. If the answer is yes, then it turns out that that means that there are no minimal generic degrees because a density 1 set can't have minimal generic degrees. This was proved by Igusa. So that would answer that question. So that is, I think, a very interesting question about. And in fact, in earlier ways that I was trying to get a minimal pair, in some sense, I would always, in the end, try to do it that way by getting it amounted to getting a non-zero generic degree. A generic degree that doesn't bound a non-zero generic degree of density 1 set, and those failed, so who knows. And so now also a couple of questions that come from this paper with Astor and Jacques. One thing that I mentioned that wasn't going to come up at all until the end is the notion of effective dense computability, effective dense reducibility. Remember, that's the one where descriptions can always have to answer, but one of the answers could be I refuse to give an answer. There we have no idea. Are there minimal pairs in the effective dense degrees? We also don't know whether there are minimal pairs for the relative effective dense computability. So Igusa's result for generic computability may or may not hold there. And so that one is completely open. Certainly it seems to me, having thought it for a while, that the technique in the construction of minimal pairs that I gave here doesn't seem like it should work for the effective dense degrees. They don't seem to have the right, that kind of idea that you can go back to a previous state and you can go back to 2 different previous states and find a compatible one. Once you have those boxes, right, that creates a potential incompatibility, so it doesn't seem to work. So that's completely open. Another thing is, remember that I mentioned that in all of the reducibilities, we were able to show that upper cones are small in the sense of measure. They all have measure 0. What about category? So non-trivial upper cones in the generic degrees are meager. We did show that. In fact, to not be on an upper cone of X, it's enough to be 1 generic relative to X. But we don't know about the other ones. Are non-trivial upper cones in the coarse dense and effective dense degrees meager? Of course, the answer is yes. Then you have a follow-up question, how generic do you need to be? But we don't even know whether they actually are. I mean, my guess is that they are. I don't know how to show them. So since I have a few minutes, I want to talk about a related, slightly different topic because there is one more question I want to talk about. Definitely unapologetically very technical question, but maybe people who are interested in algorithmic randomness stuff might be interested in it. But it comes from a fact that I think is generally interesting, which is that there are natural embeddings of the Turing degrees into each of these degree structures. So this comes out of various different papers. And when I say they're natural, basically there's a couple of properties that one could ask for, for a nice embedding of the Turing degrees, and these embeddings have it. In fact, they're unique with these properties. So there may be some like weird embedding, but as far as natural embeddings, there's only one embedding in each case. And here's one way to get it, to induce it. So what do you want to do? So basically, to replicate a Turing degree as a course degree or generic degree or whatever, what you want to do is you want to take your set and you want to encode each bit of that set in a highly redundant way, so that you end up with, like those old like holograms where you could like cut a bit of it and you still get the whole image, that kind of thing, right? You want to encode information very redundantly. So you want to take each bit and replace it by lots and lots of bits that are equal. And that's what the second thing down there goes. Now, because of issues of uniformity, because some of the, if you're trying to do the uniform versions of these reducibilities, what you need to do is you need to get each bit and you want to repeat it infinitely often first. So that's what this R does. So R of A, all it does is it takes the set A and repeats each bit of A infinitely often. And then you take these intervals, large intervals, right, between 2 to the n, 2 to the n plus 1, and you take each m in RA and replace its value by the same value in the entire interval. So now you've coded things very redundantly, and so you need to prove it, but hopefully it's believable that if I give you any course description or generic description or whatever of this set, right, I can recover the whole set. And in fact, I can do it even in a uniform way, in a sense. So that's the kind of the embedding, and it's pretty natural, right? It is the idea of just taking information in a set and spreading it out very redundant. So that one thing that this embeddings lead to is an interest in a notion of quasi-minimality. So this is something that comes up in other settings where you have Turing embeddings, like into the enumeration degrees, for example. A non-zero degree in any of these structures is quasi-minimal if it's not above any non-zero degree in the image of this embedding. So if you look only at the image of this embedding, it's there's nothing but minimal in that sense. And one way to kind of think of what a quasi-minimal degree should look like is that if you don't code information in a very redundant way, then you really shouldn't be above something that does. So there's an intuition there that typical sets should not have quasi-minimal degrees. And this, in fact, is borne out. So here's a theorem, again, combining work of several authors. One generics are quasi or have quasi-minimal degree in all of these degree structures. And also, weak 2 randoms do. So that, that does mean the intuition is correct. Now, there's an obvious question here, right? So weak 2 randoms, what about 1 randoms? And there we got that phenomenon that happens in a lot of cases where we have certain intuitions about what should happen for random sets, and they start to happen at the weak 2 random level, and they don't quite happen at the 1 random level, and it has something to do with k-trivials. And that's what happens here. Every 1 random is quasi-minimal in the uniform versions of the generic course and effectiveness degrees, but not in the non-uniform versions of all 4 of them. And this actually does have some really interesting connections with k-triviality. In the case of the course degrees, there's a connection there with some really interesting work on certain subclasses of the k-trivials by Greenberg, Miller, and Denis. That would take much time to go into that, but there is one case that's missing here, which is, are 1 randoms quasi-minimal in the uniform dense degrees? Now, I admit it's a technical question, right? But it's the one remaining case there, right? And it is possible that the answer could be interesting from the point of view of the theory of algorithmic randomness. So I wanted to mention that question as well. So that's what I wanted to say, and hopefully, some of you might get interested in some of these questions and want to work on them. And I will leave the last slide. One of the advantages of this kind of online talk is I can have a slide with really small type and people can still read it. So I'm just going to leave the slide with references here. And thank you all for your attention.
Thank you very much for this talk. Is there any question? Don't forget to unmute yourself if you want to ask any question. So I see no hands up. So actually, I've just got a question about this effectively dense computability. So you said that your technique didn't work to prove that there is no minimal pair in the non-narrative, but in the reduction in the dense, well, the effectively dense degrees.
Yeah, we don't know.
Yes, but what about the results of Greg Guza about the non-existence of a minimal pair in the generic relative generic compatibility? So have you tried this technique? Is there yeah, is there any reason which is there exploiting anything which is not working in the case of effectively dense compatibility?
So the answer is yes, I've tried, but not enough to give up. As in, not enough to say, yeah, no, that's not going to work, So I don't, there's blockage there. There's things that I don't see how they would work, but I haven't spent enough time with it to tell you for sure that it's not going to be just, some slight clever, but it's not immediate. Like I couldn't just make it work. Right. So there are issues there. And it's been a while, so I couldn't describe them exactly what they are, but yeah. So the answer is yes in that sense, but no, not in the sense that I completely given up. Will not try again with that method.
Okay. Thank you very much. I see that Noam has a question, so you want to ask your question, Noam?
Thanks, Denis. Great talk. The proof that you outlined remind me a little bit of argument that's in a paper of mine with Ludovic, Matthew, Dan, and Rod, and also independently discovered by Arno Pauli, Kengmeng Eng, and Takayuki Kihara in their big paper about enumeration reproducibility in topological spaces. And that is that if you've got a delta 2 set, which is non-trivial in the enumeration degrees, then in the enumeration degrees, it is above a non-trivial semi-recursive set. So this is a kind of a permitting argument in the enumeration degrees of delta 2 sets, which uses very much this kind of idea that you can recover more than one stage back because they cohere nicely. So I'm wondering if this implies that like a stronger version, like you can use your techniques to show something like every density 1 delta 2 set is part of a minimal pair or something like that.
Not as far as I know, but I haven't looked at your paper, so I should look at that and see. I mean, I'm not surprised that this kind of technique is useful in other things that have to do with enumeration. I hadn't seen it before, but no, I should definitely look at that. I mean, I did try obviously to extend things and see, but yeah, I should look at that. Thanks.
Okay, is there any other question? I don't see other hands.
So let's see. Can you get your sets in your minimal pair and the generic degrees to be at some finite level of the Hirschfeldt hierarchy?
Oh, that's a good one. Yeah, finite level. Not as far as I know. I mean, obviously, I'm sure that they're like omega, whatever. I was going to say omega C, but I would offend no omega CA. But finite level, not as far as I know. Yeah, I don't see an obvious way to do it, but I haven't tried specifically.
Okay. Any other question?